Welcome to another deep dive, and today we're going to be looking at something pretty cool. We're talking about pendulum waves.
Oh, yeah, pendulum waves.
Have you ever heard of pendulum waves?
I have.
They're pretty wild.
They are.
So we've got some cool resources today, like always. We've got a link to an actual YouTube video of pendulum waves so you can see what we're talking about.
Yeah, you got to see it to believe it.
But then also, we have this really neat simulation applet.
Yeah.
Where you can actually play around with different lengths of pendulums and see the waves form.
That's right.
It's called the Amazing Pendulum Wave Effect JavaScript Model Simulation Applet HTML5.
Okay.
From Open Educational Resources, Open Source Physics at Singapore.
Nice.
So it's a pretty neat simulation applet. You can run it on just about any computer, any phone, any tablet.
That's fantastic. Everyone can play along at home.
Yeah. So let's talk about pendulum waves. So basically you have a row of pendulums.
Right.
And they are incrementally longer than the last one. And they start swinging.
Right.
What happens?
Well, they start swinging, and because they're all slightly different lengths, they all have slightly different periods of oscillation, right?
Okay.
And what that means is they all swing at different speeds. And so at first they're all together, and then they start to spread out, and then they come back together, spread out, and come back together, and it makes these amazing wave patterns.
Okay, so why does the length of the pendulum determine how quickly it swings back and forth?
That's a good question. It all comes down to the physics.
Yeah.
You can think of it like this. A longer pendulum has a longer distance to travel in each swing. And so it takes longer for it to complete one full cycle, right? Like a longer swing set at a park takes longer to swing back and forth than a shorter swing set.
Okay, yeah, that makes sense. So it's like all about that distance that it has to travel.
That's right. That's right. And so when you have a whole bunch of pendulums next to each other with slightly different lengths, you're basically creating a series of swings with different swing times. And as they swing, those different swing times cause them to fall in and out of sync with each other.
Oh, okay.
Creating those visual waves that we were talking about. It's really amazing to see.
Yeah, so in the simulation, which is super cool, you can actually go in and change the lengths of the different pendulums.
Oh, yeah.
And you can see how that affects the wave pattern that you're seeing.
Absolutely. And that's really the fun part, is you can play around with it.
Yeah.
You can adjust the length, you can adjust how many pendulums there are, and you can see these different intricate patterns emerge.
Oh, that's cool.
Yeah.
So is this just a cool visual trick?
No. It's so much more than that.
Oh, okay.
Like, yes, it's visually stunning to watch these pendulum waves form, but what's really fascinating is the underlying principle that it demonstrates.
Okay.
The idea that small differences can lead to really complex emergent patterns.
Right. Yeah.
It's a simple system, right?
Yeah.
It's just pendulums. But the way they interact with each other creates this incredibly intricate and dynamic behavior.
Okay.
It's a reminder that complexity doesn't always require complicated ingredients. Often, it's the subtle interactions between simple elements that give rise to something truly remarkable.
So this seemingly simple system, like you're saying, it's just pendulums and strings and gravity, but it connects to these deeper scientific concepts.
Exactly. It's a microcosm of a lot of things that we see in the world around us.
Like what are some examples of where we see this in the real world, this concept of small differences leading to big changes?
Well, I think a really good example is traffic patterns.
Oh, okay.
You know how you get those traffic jams? Seemingly out of nowhere?
Right.
Sometimes it's just a small fluctuation in the speed of one car that can ripple down the line and cause this massive slowdown.
Oh, wow. That's pretty crazy.
It is.
So it's like each car is like a pendulum, and the speed of the car is like the swing of the pendulum.
Yeah, you can think of it that way. And just like those tiny differences in pendulum length create those dramatic wave patterns, those small variations in car speed can create these huge traffic jams. It's really remarkable.
That is wild. I'm really starting to see how this principle applies in so many different areas. It's not just about pendulums. It's about a way of thinking, a way of understanding how complexity emerges from simplicity.
Exactly. And that's just the beginning. Like, we haven't even touched on the implications of this principle in fields like biology, economics, or social systems.
Oh, wow. Yeah, there's so much more to explore here. And speaking of exploring, we have a whole bunch of other resources linked in the show notes that hint at some pretty cool connections to even more complex concepts.
We do.
There's one, for example, on something called the conical pendulum. What is that all about?
Ah, the conical pendulum. It's another fascinating type of pendulum motion, but instead of swinging back and forth, it moves in a circle.
Wait, a pendulum moving in a circle? How does that even work?
Well, it's a bit different from the regular pendulum we've been talking about. With the conical pendulum, the bob, that's the weight at the end of the string, it's swinging around in a horizontal circle rather than a vertical arc. And as it does that, the string traces out a cone shape.
Oh, okay, so it's like the pendulum is spinning around instead of just swinging back and forth.
Exactly.
That's pretty wild.
It is, and the physics behind it is a little bit more complicated, involving things like centripetal force. But the underlying principle is still the same. The length of the string and the speed of the bob determine the shape and size of that cone.
So we've got simple pendulums making waves and clinical pendulums spinning in circles. And you said earlier that these principles apply beyond the world of physics. I'm starting to see how deep this rabbit hole goes.
It definitely does. And the coolest part is that by understanding a seemingly simple phenomenon like pendulum waves, we can unlock a much broader understanding of how the world works.
Okay, this is already blowing my mind. But before we dive into all the other resources and those connections to other fields, let's take a step back and talk about the real aha moment with these pendulum waves. Like, what's the biggest takeaway here?
You're right. Let's crystallize that. I think the real beauty of observing these pendulum waves is that they provide this powerful visualization of how complexity arises from simplicity. You know, you look at these pendulums, they're all slightly different lengths. Those differences seem so small at first glance.
Right.
But then as they start to swing, they create these captivating, intricate patterns.
Yeah.
And it's a reminder that sometimes the smallest variations, when amplified over time, can lead to profound and often unexpected outcomes.
That is a fantastic way to put it. It makes you realize that those tiny differences, those subtle variations, they can have huge consequences. Now, but how does this actually apply to things like biology, economics, or social systems?
Yeah.
How can we use this knowledge to understand and maybe even solve problems in these areas?
That's a great question, and one that we'll explore more deeply in just a moment. But before we do, I want you to think about this. Where else have you observed this principle at play in your own life or work? What small differences have you seen that have led to big changes?
That is a good question to think about. It's something to ponder as we continue our deep dive into the fascinating world of pendulum waves and the profound lessons they offer.
Exactly.
All right, so we've just scratched the surface of how this small differences lead to big changes thing plays out in the real world. You mentioned biology and evolution earlier. What are some other examples where we see this?
Well, let's think about compound interest.
Okay.
It's like a classic example, right?
Yeah.
How small, consistent actions over time lead to substantial results. Like even a small amount of money invested regularly can grow exponentially over decades thanks to compounding.
Okay, so that makes sense. It's like those tiny differences in the pendulum legs, right?
Yeah.
They seem insignificant at first,
Yeah.
but over time, they create those big dramatic wave patterns.
Exactly.
So in the case of compound interest, it's those small, regular contributions that build up over time.
Yeah, exactly. And this principle isn't just about positive growth either.
Oh, okay.
Think about debt, right?
Uh-huh.
Small, unmanaged debts can snowball into these huge burdens if you just leave them unchecked.
Mm-hmm.
It's a powerful reminder that even seemingly insignificant financial decisions can have really long-term consequences.
Wow, that is a sobering thought. So it's like a double-edged sword.
Kind of.
Small actions can create these big positive changes, but they can also lead to big problems if we're not careful.
Exactly, yeah. It highlights the importance of being mindful, even of those choices that seem really small in the moment.
Yeah, for sure. Okay, so we've talked about compound interest and debt. What about social systems?
Oh, yeah, great point. Think about how ideas or trends spread. A small group of people with like a new idea or a new way of doing things, they can, under the right conditions, influence larger and larger populations. What starts as a fringe movement can eventually become totally mainstream.
That is so true. Social media is a perfect example of that, right?
Absolutely. It's like ideas can spread like wildfire online, you know?
Yeah.
Turning small voices into these powerful movements.
Wow, yeah. It's crazy to think about how these things can take off and become so big. So just like with our pendulum waves, it's tough to predict which small differences will actually lead to those large-scale shifts. complicated one.
Yeah, there's a lot of factors at play. It's hard to predict exactly how things will unfold.
Okay, this is all pretty mind-blowing. We've gone from swinging pendulums to compound interest to social movements, and it's all connected by this underlying principle of small differences leading to big changes. But I got to ask, like, how does this actually help us? What can we do with this knowledge?
It's a good question. I think it serves as a reminder to pay attention to the details, to recognize that those seemingly insignificant variations can have huge consequences over time. It's a call to be more mindful, you know?
Yeah.
Think about the long-term implications of your choices.
Right.
Consider the ripple effects of even small changes.
So it's not just about understanding this principle. It's about applying it to our own lives.
Exactly. It encourages us to think systemically,
Okay.
to see how things are interconnected. A small change here can ripple outwards, impact the larger whole. It's about understanding that nuance matters, you know?
Right.
Sometimes the most profound changes come from unexpected places.
This is making me rethink my entire approach to problem solving. Instead of just focusing on the big, obvious issues, maybe we need to consider those subtle factors that might be driving the change.
I think that's a really insightful point.
So it's like a shift in perspective, right?
Totally. A way of seeing the world differently, with more awareness of how even the smallest actions can accumulate over time.
Okay, this has been incredible. We've covered so much ground already. But there's one resource that really caught my eye that we haven't talked about yet. It's called Molecular Workbench.
Oh, yeah.
What is that about?
Molecular Workbench is a really fascinating tool for visualizing and understanding things at the molecular level, and it actually ties in perfectly with our discussion.
Wait, so you're saying those pendulum wave principles apply even at the molecular level?
Absolutely. Just like those pendulums, right? They have different swing periods based on their length. Well, molecules vibrate at different frequencies based on their energy levels.
So it's like those pendulums, but instead of swinging, they're vibrating.
Exactly. Imagine like these tiny little springs within each molecule constantly stretching and compressing.
Okay, wow.
And just like those tiny differences in pendulum length create those complex wave patterns, these small variations in molecular vibrations can have huge effects on how molecules interact with each other.
So now we're getting really, really small. But how do these tiny vibrations actually affect things? Give me some examples.
Sure. For one, they can influence chemical reactions.
Okay.
Imagine two molecules are colliding, right? If they're vibrating at just the right frequencies, their energy can transfer more efficiently,
Okay.
make the chemical reaction more likely to occur.
It's like those molecules are dancing, and if they're in sync, they can get things moving.
That's a great analogy.
And it's not just about chemical reactions, though. Right?
They're not at all. These vibrations play a role in the properties of materials, too.
Okay.
For example, how a material absorbs and reflects light is actually influenced by the vibrational frequencies of its molecules.
Hold on. Are you saying that the color of a material is related to how its molecules are vibrating?
It is, yeah. And it goes even deeper than that. The way a material conducts heat or electricity, its melting point, how strong it is, all these properties are influenced by those tiny molecular vibrations.
So we can actually manipulate these vibrations, too.
Yeah, we can. We can use things like lasers to change the properties of materials by manipulating those vibrations. It's pretty amazing.
So it's not just observing these vibrations, it's actually about controlling them to create new things.
Exactly. And that's where things get really exciting in terms of developing new technologies and materials. But I have to ask, how did scientists even figure all this out? It seems like we're talking about things that are way too small to see.
That's a good point. And that's where tools like the Molecular Workbench come in.
Okay.
They let us create simulations and visualizations of these molecular interactions, giving us insights into this world that's normally hidden.
So it's kind of like having a super powerful microscope that lets us see those tiny molecular dances.
Yeah, that's a great way to think about it.
So we've gone from these macroscopic pendulum waves to the microscopic world of molecules. It's incredible how this one principle, small differences leading to big changes, connects all these different areas of science. It really is. It shows how interconnected knowledge is, and it highlights the power of scientific inquiry. You know, we start with something simple, like pendulum waves, and we uncover this fundamental principle that operates on every level of the universe. And then we have these tools like the Molecular Workbench that let us explore that principle more deeply, opening up new possibilities for understanding the world.
This has been an awesome journey, and I'm still processing all of this information. But we still haven't really dug into this Molecular Workbench thing.
True.
I'm really curious to learn more about how it works and what we can actually see with it.
Yeah, me too. I think it deserves its own deep dive.
Okay, so let's do it. In the next part of our deep dive, we'll delve into this molecular workbench and see how it can help us visualize and understand the world at the molecular level. I'm really excited to see what we can uncover.
Me too. It's going to be cool.
Okay, so we talked about how this idea of small differences lead to big changes plays out in everything from physics to economics. But now I'm ready to actually get my hands dirty with this molecular workbench you were talking about.
Yeah, let's dive
Can
in.
we really visualize these tiny molecular vibrations using this tool?
Oh, absolutely. The molecular workbench is like a virtual lab. It lets us zoom in and see the world from a molecule's point of view. We can actually model those tiny vibrations and see how they affect everything from the properties of matter to biological processes.
Okay, so I'm picturing like a super powerful microscope that lets us see atoms and molecules moving around. Is that what we're talking about?
It's a great way to think about it. We can't see these vibrations directly, but Molecular Workbench uses computer models to represent them visually. We can actually see how they influence chemical reactions, material properties, even how proteins fold.
Okay, so walk me through it. How does it actually work? What kind of things can we do with molecular workbench?
Well, first off, we can actually build molecules virtually, like atom by atom. We can change the types of atoms, their bonds, and we can even add energy to make the molecules vibrate. It's like playing with a molecular building set.
That sounds kind of fun, actually, but how do we actually learn from this? What kind of insights do we get by messing around with these virtual molecules?
Here's where things get really cool. Let's say we want to understand how temperature affects a chemical reaction. We can model the molecules in Molecular Workbench, and then we add heat, basically making the molecules vibrate faster. Then we can actually watch how those faster vibrations make the molecules collide more often and with more energy, which speeds up the reaction.
So we're actually seeing those small differences in vibrations lead to a big change in how fast the reaction happens.
Exactly, and it's not just limited to chemical reactions either.
Okay.
We can use Molecular Workbench to look at how vibrations determine the properties of materials too, for example. We can model a metal and see how vibrations affect its ability to conduct electricity.
Wait, are you saying that how well electricity flows through something like a wire is related to how much its molecules are vibrating?
That's right. Those vibrations can actually slow down the flow of electrons, creating resistance. And get this, by changing those vibrations, we can actually change how well a material conducts electricity. That's the idea behind some really advanced tech like superconductors.
Wow, okay, now I'm seeing how powerful this tool really is. We're not just watching these vibrations, we're starting to see how we can control them to design totally new materials and technologies. It's like we're unlocking a whole new level of control over the world around us.
Exactly, and it goes even further than that.
Oh, wow.
Molecular Workbench can even be used to study biological systems. We can model proteins, for example, and see how vibrations affect the way they fold and interact.
Wait, so those tiny vibrations are important for something as complex as how a protein folds.
Those vibrations can actually help proteins fold into the right shape, which is super important for them to work correctly. And, when proteins misfold, it can lead to diseases like Alzheimer's and Parkinson's. So understanding these vibrations could be huge for developing new treatments.
This has been an amazing deep dive. We've gone from swinging pendulums to watching molecules dance. It's incredible how this one principle, small differences leading to big changes, connects so many different areas of science.
It really is. It shows you how everything is connected and how powerful scientific exploration can be by starting with something as simple as a pendulum. We've discovered a principle that works at every level of the universe, and tools like Molecular Workbench give us this amazing way to explore it even further. It opens up so many new possibilities for understanding and even changing the world around us.
I'm walking away from this with a whole new appreciation for the power of tiny things. Who knew those subtle differences in vibrations could have such a huge impact?
It's a good reminder that sometimes the biggest changes start with the smallest steps, and it's a challenge to us to look deeper, to explore those hidden patterns and connections that make our universe so complex and amazing.
That's a great way to wrap things up. A huge thank you to our expert for guiding us through this fascinating journey. And to our listeners, I encourage you to keep exploring those tiny wonders, those small differences that make our universe so intricate and beautiful. Who knows what amazing things you might discover along the way.